Hello everyone, and welcome back. This is 5.3, which is a section on linear programming in 2 dimensions, a geometrical approach. And I first want to start off this section by going over an example very similar to the example we left off on 5.2. And I know it looks like a lot, it's pretty overwhelming honestly, it's a long question. A lot of these questions we'll be seeing in this section will be long, but we'll be diving into it from a different approach, from a geometrical approach actually. And the problem will not be that difficult to solve so long as we have things labeled correctly. That's the biggest step, is labeling. So let's take a look at this. Let's see if we can label a few things. So the example says the manufacturer of tents makes 2 models, the standard model and the expedition model. The standard model requires 1 labor hour for cutting and 3 labor hours for assembly, where the expedition model takes 2 hours to cut and 4 hours to assemble. All right. The max labor hours available per day for cutting and assembly are 32 for cutting and 84 for assembly, respectively, just means in that order. So notice cutting comes first, 32 comes first, assembly comes second, and 84 comes second. So 32 corresponds to cutting, 84 corresponds to assembly. Good. If the company makes $50 of profit on each standard model and $80 in profit on each expedition model, how many of each should be manufactured on a given day to maximize daily profit? So it's going to be a little difficult to label these things. So here's what I'm going to do. I'm going to erase this and I'm going to reorganize all of the given information in a table. Okay, so this is the table I was referring to earlier. So notice we have standard model, expedition model. We have the labor hours for cutting for each of them, assembly for each of them, the max labor hours per day for cutting and for assembly, and the profit for each of the models. All right, so now what I'm going to do is I'm going to build a system of inequalities based on this, and it's going to be fairly straightforward how you do that. So let me just say we have x plus 2y. X plus 2y represents the cutting hours. So what I'm doing is I'm multiplying every hour it takes, every 1 hour it takes for each standard model to cut, plus the same thing, cutting hours for expedition models. So I'm basically just multiplying these numbers by x and y. So notice I'm calling the standard models x and the expedition models y. And for cutting, we want this total result to be less than or equal to 32, because that's the maximum of labor hours we have available to us. So very similarly for assembly, what are we going to do? We're going to multiply 3 by x and add that to 4 times y. And that's going to be less than or equal to our assembly hours we have available to us, which is 84. The next thing, like we saw in the previous section, is x and y are each going to be bigger than or equal to 0 because, well, x and y represent the amount of standard and expedition models we manufacture, and we don't manufacture negative amounts. We can manufacture 0, meaning none of them, but in this case, they're going to be bigger than or equal to 0. Also, just to make things a little quicker on us and easier for us to write down so we don't write too much, I'm going to instead write this in a different notation, a different way. I'm going to write this as x comma y bigger than or equal to 0. And these are what are known as non-negative constraints. Okay. The next thing is that we have this profit that I've kind of touched on a little bit. Profit, there is a profit equation. So let me call P our profit for however many models we manufacture of each one. Well, if you manufacture X standard models and Y expedition models, you make $50 on each standard and $80 on each expedition, then the profit for that amount will be whatever 50 times X is plus whatever 80 times Y is. Of course, depending on what X and Y are. We're attempting to maximize this given these constraints. So what we're going to do is the following. We're going to graph this region. So this system of inequalities can be graphed, and the region of its solutions is called a feasible region, or the feasible region. So it's a region like we graphed in the previous section, but I'll call it a feasible region. Okay. Oh, by the way, this profit equation here is known as the objective function. So there's a lot of vocabulary in this section which will kind of help us talk about certain things. But yeah, so here's what we're going to do. We're going to graph the region given these constraints. So I'm going to lift this up and I'll graph it over here. And then we'll talk about what point in that region will correspond to a maximum profit. So we'll see that right now. All right, so to graph the region, we need to graph these lines, pretending they're equality, we'll get lines, and then we'll shade in the corresponding part of that line, the corresponding side of that line. Also, remember that x and y being bigger than or equal to 0 means that we are in the first quadrant, which is where x is positive and y is positive. So that makes sense. Okay. Now to graph these lines, I kind of spoke about this also in the last section. There's a quick way to graph a line to find the x and y intercepts. So for the first one, if we let y equal to 0, the x-intercept will be 32. Just imagine these are equality for a moment when it comes to graphing the lines. So x is going to be 32. So let's say 32 is over here somewhere. It's not going to be to scale, but that's fine. So x is equal to 32. What's y going to be equal to? Well, when x is 0, to find y, divide by 2. 32 divided by 2 is 16. And let's just say that that is over here somewhere. Connecting these points gives us this line. And if I call this equation 1, or inequality 1, that'll correspond to the line of that inequality. Okay, we have one more. So again, I'm going to do the same thing. Divide by the number in front of x, divide by the number in front of y. So again, when you let y equal to 0, to find x, all you have to do is divide the other side 84 by 3. 84 divided by 3 is, I believe, 28, which will be a little less than 32. Let's just say it's here. 28. And the y value will be, well, let's see. When x is 0, the y-intercept is going to be 84 divided by 4, which is 21. So 21 is a little bit above 16. Let's just say it's over here. Connecting these 2 points gives this line. And I'll call this inequality 2. So I'll label its corresponding line with that point, or with that label. So notice we have a point of intersection here, and this is a corner point. Also notice these inequalities are each less than. So we're going to shade below. And remember also from the previous section, if there was a negative in front of this y, then the sign would flip when you get y by itself. Since these are both positive and they're less than, then that means we shade below the line. Below each of these lines will correspond to this feasible region. And we have 4 corresponding corner points. Okay? Great. Now what? Well, so any solution to this inequality system of inequalities, will be in this region. And we want to find a solution, an x, y values, which represent the amount of standard and expedition models we'll manufacture, plug them into this and see which one will yield a maximum profit. And you can play around with it by picking points, but I'm going to tell you right now that the only ones we really care about are the corner points. So I'm kind of skipping through some detail there, but again, you can try to do that yourself, pick points in this region, but you'll find out that the corner points are the only possible the only possibilities basically, where you'll end up with either a maximum or a minimum. By the way, a maximum or minimum for our objective function is known as an optimal value. So optimal value is either max or min. So just keep that in mind. And in this case, our optimal value is max because we're asked to maximize profit. So we're going to plug these corner points in. So let me make this table for us. So we have these corner points. And then we have our objective function p. So what are our corner points? We have 4 corner points to plug in. So we have 0, 16 up there. We have 0, 0 here in this corner. And then this corner point is 28, 0. And then finally we have the most interesting of them all, where they intersect. Now, where they intersect, I've also shown you how to find this from the last section. You set the equations equal to each other by, well, you don't set them equal to each other, but you solve the system is what I mean to say, of equations. So if we consider, write this a little differently, I guess like this, the system of equations, I guess I need to move this, there we go. The system of equations as equalities, well, notice multiplying the top by -2 will make this y -4y, and then these will eliminate. We could alternatively multiply the top by -3 so that the x's cancel, but I'd rather multiply by 2 than 3. It doesn't matter. You can do it the other way around. So multiplying the top by -2 gives us -2x minus 4y is equal to, because we're pretending they're equality when we solve when they intersect. Let's see, what's -2 times 32? It's -64. And then the bottom one stays the same because we want the y's to cancel out. So it's 3x plus 4y is equal to 84 because we want equality for the point of intersection. Okay, eliminating the y's, -2x plus 3x is just x, and 84 minus 64 is 20. So the x value is 20. Perfect. What's the y value? Well, plugging this into, let's say, equation 1, we get x plus 2y is equal to 32. Since x is 20, we get 20 plus 2y is equal to 32. All we have to do now is subtract 20 and divide by 2. Subtract 20, we get 2y is equal to 12. And then finally divided by 2, we get y is equal to 12 divided by 2, which is 6. So the point is 20,6. And again, it's not to scale. If we tried to write it to scale, then the point would look more like what it actually is. But this corner point is indeed the point 20,6. And again, all we're going to do now is plug these into our objective function, and I'm going to try to do that here. Let's see. So when x is 0, we get 0, plus, what's 8 times 16? Well, I want 80 times 16. But I believe we're going to get, let me think about this for a second. So I'm getting 1280. So you can check me on that, but that's what I got. When we plug in 0, we get 0 plus 0, which is just 0. When we plug in 28 and 0, we get 28 times 50 plus 0 times 80. 28 times 50 is 1400, I believe. And now finally plugging in 20 and 6, let's see what we get. Well, when we plug in 20 for x, I'm getting 1,000. And then 6 times 8 is 480. So that's 1,000 plus 480 with a, plus 480. So that's going to be 1480. Good. And now which one of these is the maximum, which one of these is the minimum? So notice the largest number here is this guy, 1480. So that is indeed our max. And our minimum is 0. If you wanted a minimum profit, don't make any. If you want a minimum non-zero profit, then I don't know if it would necessarily be 1280. Like, just thinking about it, if you sold one of standard and zero of expedition, then you make $50 and that's it. But yes, this is how you find the optimal values, the max and mins. You just see which corner point corresponds to the largest one, that's your max, and which one corresponds to your smallest one, that's the min. But this question was asking to maximize profit, so our answer is this. So to summarize things, our max profit is $1,480, and that happens when you sell or when you manufacture So in other words, to make this profit, you have to manufacture how many standard and how many expedition models. So we need to, so remember, X and Y. X in this case was standard and Y was expedition. So we need to manufacture 20 standard models and 6 expedition models. And that's our answer. Great. So again, it was a little bit of a process, of course, but we're going to do our best to talk about the details of what we did and how to get a better handle on this process. Okay, so here I have listed a few things that we're going to be using in this section. And in fact, we use them in the last problem that we just did. And that problem really is what linear programming is all about. That's what we're going to be doing in this section. And yeah, so if you remember what that was, really what we're doing is we are finding either a max or min, which is called an optimal value, of an objective function in a particular feasible region, which is the region of our constraints, which is basically a system of inequalities. So you have a system of inequalities set out, you plot the feasible region, shade it, you find corner points of that region, plug them into the objective function and see which one's a max and which one's a min. Okay, so let's read these theorems here. First one is called the fundamental theorem of linear programming, and it says any optimal value, provided it exists, more on that in a second, of an objective function occurs at a corner point of the feasible region. So exactly what we did in the previous problem. Plotted the feasible region, plugged only the corner points into the objective function to find our optimal values. Okay. Now, here's what I want to say about existence of optimal values. There's 3 parts here, so let's read. The first part reads, if the feasible region is bounded, remember what that means. It means our region is actually contained between lines, so it's a closed region. It doesn't go off to infinity or anything like that, unlike unbounded, but we'll get to that. Then both max and min exist, again, if it's bounded. However, if it is unbounded, then, well, actually we need a little bit more than that. So let me say, if the feasible region is unbounded and the coefficients of the objective function are positive, then only a minimum exists. Third part here reads, if the feasible region is empty, meaning there is no feasible region, it may just be like a point or something like that, then no optimal value exists, which makes sense because there wouldn't be any corner point for us to plug in. Just to talk a little bit more about part 2, let's say we have the following region. I guess I could graph it here. So let's say this is our region over here. We still have corner points, but it is an unbounded region. So you can plug the corner points in, and either you'll get a max or a min, but if the objective function, let's say it's p is equal to ax plus by, like we had in the previous problem, so I say here, if the coefficients of the objective function are positive, so if a and b are both positive, then this implies that p only has a min. In the feasible region. What that means is that there's no maximum. There is no maximum because any point you pick, you can pick another point that's bigger. So let's say plugging the x and y values of this point in will produce a large value of p, but some other value way out here, let's say, because the fact that the feasible region in this case is unbounded, it spreads off to infinity. So this point way out here is contained in the feasible region technically. You see that? So we can basically potentially pick any points we want to have a larger and larger value, so a maximum. We'll have to see in more problems, more examples, because it just kind of depends if we're trying to maximize or minimize, but this at least allows us to get a handle on these certain cases. And these are the only cases, so that's good. So we'll see those examples right now. Okay, so before we begin this example, I want to go over the procedure that I've mentioned previously that we applied for the previous example. And here, this procedure is this geometric method to solve linear programming problems with 2 variables, and they're called decision variables. So like x and y from the previous example are decision variables. Basically, we get to decide what those values are equal to in the end to find an optimal value, or optimal solution is what it's also known as. Okay, so here are the steps. So first, graph the feasible region of our constraints and label the corner points. Secondly, construct a corner point table that includes values for our objective function. Third would be to determine the optimal value or optimal solution for the objective function. And then fourth would only apply to applied problems, like in the previous problem, interpret. So that was the last step where I had to write a sentence, and I said the maximum profit is this when you produce this many of each model, let's say. So here, this example is not applied, it's a pure math problem, and we are asked to max and minimize z, so this is our objective function. So that's nice. So we want to find the optimal value or optimal solution subject to these constraints. So let's try to see if we can graph each of these things to get our feasible region, and then let's see what we can do. So first off, I'm going to start off by doing that. So notice we have our non-negative constraints, so I know it has to be in the first quadrant of the xy plane. Okay. Secondly, to get these lines, so I'm going to divide each x and y by, well, I guess each of this number by each of the coefficients of x and y is what I'm trying to say, to find the x and y intercepts. So remember, to find the x-intercept, you set y equal to 0. So we'll have 6x is equal to 36. Divide by 6, x is 6. So x is going to be 6. Okay. Y is going to be, when x is 0, divide by 2 to get y is going to be 36 divided by 2, which is 18. So plotting these 2 points and a line straight through them gives us this. All right, what next? Oh, next we have 2x plus 4y is, let's say, equal to 32. All right, so now let's see, dividing x by 2 to get x by itself, divide both sides by 2. 32 divided by 2 is 16 for the x value. And again, this is not to scale. To get the y value, let x equal 0 to get the y-intercept. Divide by 4, 32 divided by 4 is 8, which is down here, let's say. Connecting these points to get the line for this inequality, it'll be this. So we have our first corner point. We also have a few more things. So first off, y is less than or equal to 20. The line y equals 20 is a horizontal line that occurs at y equals 20. So let me extend this a bit. There we go. Let's say 20 is here. Again, not to scale. So y equals 20 is this horizontal line. Good. But now what do we graph? What do we shade? Well, for the first inequality, that was this line, we're going to shade above because it's greater than. Remember, when there are pluses in front, it's equal to this. If there's a negative in front of y, then the symbol flips, so it would be below. But since there's a plus in front of y, it is greater than. So we shade above each of these lines, actually. So above both of these lines would be something like this. Good. Also, it says y is less than 20, so we're going to be below this line. Great. So this is our feasible region. Perfect. Good news and bad news. Bad news is that it is an unbounded region. It goes off to infinity like that. It is indefinite. The good news is that, well, we still have a minimum. So if you remember, since the region is unbounded and since each of our coefficients for our objective function are positive, there is no maximum but only a minimum from the existence on objective values theorem I gave you earlier. So we only have these 4 actually corner points to plot. 0, 20, 0, 18, whatever this point is, and then 16, 0. So let's see if we can label each of these in a corner point table. So we'll do that right now. I guess I'm gonna have to find out what this corner point is. We'll also do that right now. So let me erase this and move things around. So here I have things shifted around like I said I would, and I guess the biggest thing we have to do now is find this corner point. So to find that corner point, we're going to consider where these two lines intersect, And to find that point, we're going to solve the system of those two equality versions of these inequalities. So we're going to consider the system of 6x plus 2y is equal to 36, and 2x plus 4y is equal to 32. So one thing I can actually do here is divide the bottom by 2, and that'll be 2y. They can all be divided by 2, so we can do that. In fact, I'm going to make it negative by dividing by negative 2. So really I'm multiplying the second one by negative 2, well, 1 over negative 2, and we get the following system. The top stays the same, 6x plus 2y is equal to 36. The bottom now, though, is negative x. 4 divided by negative 2 is negative 2y, and 32 divided by negative 2 is negative 16. Adding straight down, the cancellation of the y's, we get 5x is equal to 20, dividing by 5, we get x is 4. Good. So we have the x value. How do we find the y value? Plug it back into either of these. Let's plug it into the top one, doesn't matter. But into the top equation now, plugging x equals 4 into the top equation gives us 6 times 4, which is 24, plus 2y is equal to 36. Okay, subtract 24, divide by 2. 2y is equal to 12, divide by 2, we get y is 6. So this point is 4, 6. So that's 4. And this value is 6. Okay, good. I've used a lot of space here, so let me erase this and write the actual table for the corner points. Right, so here's our table. Now the corner points are, I'm going to go in this order, downward. So this point is 0, 20. Right below that we have 0, 18. The one we just found finally, 4, 6. I said finally, but the last one really is 16, 0. Perfect, so these are our 4 corner points, and now we're going to plug them into z. This is our z value, our objective function. So when x is 0 and y is 20, we get 0 plus 400. Good. When x is 0 and y is 18, we get 18 times 2 is 36, so it's going to be 36 with a 0, or 360. Great. When x is 4 and y is 6, let's see, we get 40 plus 120, that's 160. And when x is 16 and y is 0, we get 16 times 10 is 160, plus 0 is also 160. Now notice, this is an unbounded region. What does unbounded imply? Unbounded and positive coefficients, which we have. But there are no negatives in our z equation, it's only positive. Unbounded region, feasible region, and, so let me write that, feasible region. There we go. Unbounded feasible region and positive coefficients imply that we only have a minimum and no maximum. Only have a minimum, we don't have a maximum. So there's no max. Okay, unfortunately. There is a minimum though. And what is the smallest value we have here from plugging in our corner points? It's 160. So we have a tie, which can happen. So our minimum is z is equal to 160, and this occurs at 2 different points, 4, 6, and 16, 0. So that's our answer there. We both maximize and minimize the objective function, and that's it. Just plot the feasible region of our constraints, our system of inequalities, find the corner points, plug them into a table, find z. The smallest is the min, the highest the max. But since it's unbounded, well, we can have an increasing amount of z's, or values of z's. So there's no max, it's unbounded. There can be larger and larger and larger values of z's. So there we go. So that was it for this example. I think we're going to do one more example, and that'll be it for 5.3. Okay, so for this problem here, this is an example from the book that I wanted to do. It was a little much to write on the board, so instead I'll just present it to you like this, and we'll read a few things here. So it says a hospital patient is required to have at least 84 units of a drug A and 120 units of drug B each day. Assume an overdose of either drug is harmless, so you can give them as much as you want, basically. Each gram of substance M contains 10 units of drug A and 8 units of drug B, and each gram of substance N contains 2 units of drug A and 4 units of drug B. Now, suppose that M and N contain an undesirable drug D, 3 units per gram in M and 1 unit per gram in N. How many grams of each substances M and N should be mixed to meet the minimum daily requirements and simultaneously minimize the intake of drug D? How many units of the undesirable drug D will be in the mixture? So here's what we're going to do. I'm going to create a table of everything in this problem labeled and just organized nicely in the table, and we're going to go from there. All right, so here's a table from the problem that we just went over. I know it was a lot of information to look at, but once everything is gathered in the table, it's a lot easier on the eyes. Notice we need an x and y variable, so let's call M our x variable and substance N our y variable. And we actually have a system of inequalities, our constraints. Notice 10x plus 2y is going to be less than 84 for drug A. So we want, there's 10 units per gram of drug A and M, substance M, 2 units per gram of drug A and substance N. So we need a minimum daily requirement of 84. So I kind of misspoke when I said less than or equal to. It should be greater than or equal to, because the smallest amount we can have is 84. So it's greater than or equal to. So it's different for here because it's minimum. Okay. Similarly, for drug B, we can have 8 of M, so it's 8 times the amount of M we're calling X, plus 4 units per gram of drug B for N, so plus 4Y, Y is the amount of N, and the minimum there, greater than or equal to, is 120. Also, X and Y are non-negative, because you cannot have negative amounts of a drug, right? That's it for the constraints. Now we have what we're trying to maximize or minimize. So we want to minimize the amount of drug D that we're administering. And if you take a look at this, this basically says that our objective function is D is equal to 3x plus 1y, or just 3x plus y. So that's our objective function. So we're going to plot the feasible region, graph the feasible region, and then we're going to find the corner points, plug them into this, and see which one's the minimum, because we want to minimize D. Alright, so let's just jump right into it. Here I have the constraints, our system of inequalities, and our objective function, and I'm going to graph our feasible region. Of course, it's in the first quadrant because we have non-negative constraints. And now just these lines is what we need to graph. So the first one, if we divide by 10 to get the x value, 84 divided by 10 is 8.4. So that should be, let's just say this is 8.4. Okay. When you divide by 2 to get the y value, 84 divided by 2 is 42. So I kind of hesitated for a second there. It's 42. So passing through x equals 8.4 and y equals 42 is this line. And I know not to extend to the negative sides because we have non-negative constraints. Okay, for the second line, dividing by 120, well, let's see. X would be equal to 120 divided by 8. I said divided by 120, but dividing 120 by 8 is what I meant to say. Let's see, if you divide by 4, 120 divided by 4 is 30, and 30 divided by 2, or 8 divided by 4 is 2, so 30 divided by 2 is 15. So that'll be 15 for the x value. The y value would be 120 divided by 4. When x is 0, 120 divided by 4 will be y. And that's, of course, just going to be 30. So that's about here, let's say. Perfect. So now we have this corner point. Also, since each of the inequalities have a plus inside of the y value, then we go above because they're both positive. So I'm going to shade above for each of the lines. So we have this shaded region as our feasible region. Notice it is indeed an unbounded region, and the coefficients of our objective function are each positive. 3 and 1 are the coefficients. So what that means is since we have an unbounded region, then we only have a minimum. And we want to minimize d anyways, so that's fine. So all we need to do now is find out what the corner points are. There are only 3 of them, and plug them into d and figure out which one's the minimum. So I'm going to erase this right here, and let's do that. So to create a table here, we have points, our corner points, and we have our value d. Now we have 3 corner points only, 0, 42. This point, which we don't know yet, I'll find that out in a second. And this point here is 15, 0. So remember how to find a point where 2 lines intersect. Solve the system of those 2 lines with equality. So we're going to solve the system. 10x plus 2y is equal to 84. 8x plus 4y is equal to 120. And you know what? Here's what I'm going to do. I'm going to divide through by 2 in the first one and by 4 in the second one, just to clear things up a bit. So the first one divided by 2, you can divide every term by 2. You get 5x plus y is equal to 42. Dividing the second equation every term by 4 gives us 2x plus y is equal to 30. And now we can just do top minus bottom. So if we do top minus bottom, the y's cancel out, notice. So we end up with 5x minus 2x is 3x, is equal to 12 minus 30 is, 42 minus 30 is 12. Divided by 3, x is 4. Good. But now what's y? Well, we can take this equation here, after dividing the bottom equation by 4, so that's 2x. Remember, x is 4, so 2 times 4 is 8, plus y would be equal to 30. Subtracting 8 would make y 22. So this should be 22 on the y value and 4 for the x value. So this corner point is actually 4, 22. Great. So now let's actually plug them into D and figure out which one is the minimum, because we want a minimum. We only have a minimum here because it's unbounded. Okay. When x is 0 and y is 42, we have 3 times 0 plus 1 times 42, so D is 42 only. When x is 4 and y is 22, we'll have 4 times 3, which is 12, plus 1 times 22, so that's going to give us 34. Okay, when x is 15, we have 15 times 3 is 45, plus 0 times 1 is 0, so we have these values here. And notice the smaller of these is 34 indeed. So the actual minimum value for D is 34, and that happens when you have 4 units of the M substance, and then 22 of the N substance. But it's not units. I guess it would be in grams. So let me just say here that minimum value of D is 34 units when we have 4 grams of substance M and 22 grams of substance n. So the last step here was us interpreting our results. If it was not a application problem and it was just a pure math problem, then we can just say the minimum is 34 and it occurs at this point. But here there's actually context. And the context is that this right here, our minimum, corresponds to the amount of units of D, and the XY values here corresponds to the amount of grams for M and N respectively. Okay, so that was it for 5.3. It was a pretty, I guess, big idea, but the way we solve is pretty simple. Just a 4-step process. Really, it's a 3-step process if you don't include interpreting and creating your models, which I think is probably the biggest struggle for everyone here, is to actually construct the model and interpret your answer. The math part I don't think we'll have a problem with. Just plotting the shaded region and finding the corner points, plugging the corner points into the objective function, looking for either the max or the min depending on the problem. Alright, so I hope you enjoyed 5.3, and that was it for chapter 5. There's no more chapter 5 now. And I'll move on to chapter 6. Things are going to get a little more hairy, but we'll handle that bit by bit, and I'll see you in the next videos. Thanks for watching.